In today's lecture, we will be discussing about how to approximate areas using three types of approximation: the right endpoint approximation, the left endpoint approximation, and the midpoint approximation. And let's try to understand each of them. So we'll begin with the right endpoint approximation. So we have a function f of x. Our goal will be to determine the area under the curve and between the interval a and b. For this, what we will do, we will divide the area into small rectangles of equal width. So let's do that. So let's divide this into rectangles of equal width. Now that we have rectangles of equal width, we'll consider that the width of each rectangle is delta x. Now delta x can be obtained by subtracting the endpoints and dividing it by the number of rectangles n. So this is going to be the value of delta x. This is not exactly a rectangle because if we look at the upper width, so this is sort of curved. So what we will do, we will consider one endpoint. So this is on the right hand side of this rectangle. We'll consider this as our first rectangle. Then draw, and considering this as one of the vertex of the rectangle, we are going to form this new rectangle whose width is delta x. Then for the second rectangle, we'll consider this as the right endpoint, and then we are going to construct another rectangle. So let's complete all the rectangles. So what we'll try to do, we will find the area of each of the individual rectangle and then sum it up, and this is going to give us the area under the curve. So we'll begin with this rectangle. Let's call it 1, 2, 3, 4, 5, 6, 7, 8. So we have a total of 8 rectangles. We'll start with the first rectangle, rectangle number 1, and find its area. So area of the first rectangle, so it has a width of delta x multiplied to its height. So this height is going to be this particular height. So that is f of a plus delta x. That's because this position is a plus delta x, and the corresponding y value to this point is f of a plus delta x, and this also becomes the height of our rectangle. Then we add it to the second rectangle, rectangle number 2, whose width is again delta x. This time it is going to have a new height, so this is going to be the new height of our rectangle, and this position is a plus 2 times delta x. So we'll have f of a plus 2 delta x. So when we complete the sequence, so we have the third rectangle, it will be f of a plus 3 delta x. We can go on and on. The last rectangle will be delta x times f of a plus, so in our case it should be 8 delta x, but we are taking a general case, so this is n times delta x. So now if we take delta x as the common factor, so this will get multiplied to f of a plus delta x plus f of a plus 2 delta x plus all the way up to f of a plus n times delta x. So this is the area under the curve, and we were going to denote, this is a right endpoint approximation. We are going to denote it with the symbol r n. So this is means r. This is the right endpoint approximation, where n represents the number of rectangles that we have considered. And the more number of rectangles that we choose, then better will be our approximation. Also, one more thing. Here, when we consider the rectangle, we see that there are some extra areas that we have calculated. So that means that whatever value of area that we'll get, we are going to give us an overestimate. That means it's going to be slightly larger than the actual value. Fine. Now what we'll do, we'll go to the left endpoint approximation. Let's do that as well. So we have the same function f of x, and we want to find its area under the curve f of x within the interval a and b. So following the same steps, we are going to divide this area under the curve into n types of rectangle, n different forms of rectangle with the same width delta x. Unlike the previous example, we had a right endpoint approximation. This time we are going to consider a left endpoint approximation, meaning we will consider this, let's say this is our first rectangle. So we will consider this as a left endpoint or the vertex of the rectangle, and Based on this, we construct a new rectangle. Then for rectangle number 2, we'll consider this as our vertex of our new rectangle and then construct another rectangle. Similarly for the third rectangle, so let's complete these rectangles. So now that we have all the rectangles, let's try to find out its area. So the area will be for the first rectangle, rectangle number 1, we have delta x multiplied. So delta x is the width of the rectangle and the height will be this particular height, and this point, the first endpoint, corresponds to f of a. So we have delta x multiplied to f of a. Plus, moving on to the second rectangle, so we have the width delta x multiplied to its height. So this height will be, so we have this point a plus delta x. So its height will be f of a plus delta x. For the third rectangle, we have delta x multiplied to f of a plus 2 times delta x. And if we continue this, the area of the nth rectangle or the last rectangle will be f of a plus, we have n minus 1 times delta x. So this becomes the area, which will denote it with Ln, where n represents number of rectangle that we have chosen, and we'll take delta x as a common factor. So this will be multiplied to f of a plus delta x plus f of a plus 2 delta x goes all the way up to f of a plus n minus 1 times delta x. So this is going to be our left endpoint approximation. Now finally, let us try to understand the midpoint approximation. So we have the curve of f of x and we divide the area under the curve into 4 equal rectangles. This is going to help us understand. So as the name suggests, we have a midpoint approximation. For the first rectangle, we will consider a point that is going to lie between the endpoints a and a plus delta x. And its corresponding height will be given by, so we'll have to consider this point. So this is a plus delta x over 2. So that means we have the area given by the width delta x multiplied to its height, which is f of a plus delta x over 2. So this is for the first rectangle. Then we add it to the second rectangle. So this is our second rectangle. We have delta x. So this is going to be multiplied to f of. So we'll consider a second point here. So what we are doing is, based on this point, we are going to construct a rectangle which passes through this midpoint. So for this, we have the first rectangle. Then we have the second rectangle, whose one of the width passes through the midpoint on the curve. Similarly, we have for the third rectangle, we have considered its midpoint, and for the fourth rectangle, we consider its midpoint and construct a rectangle. And what we're trying to do, we're trying to find out the area of each of the rectangles, sum it up, and this is going to give us an estimation or an approximation for the area under the curve. So this will be a plus 3 delta x over 2 plus all the way up to the final rectangle, which will be delta x multiplied to f of a plus 2n minus 1 over 2 times delta x. Here I have missed out the 2n. So this is going to be our area obtained as a result of midpoint approximation. So this is going to give us the area. In the previous case, I missed out one point when we're considering the left endpoint approximation. So here, what we observe here, some of the area under the curve has been missed out. So that means this is going to give us an underestimate value. It's not going to give us a good estimate. Its estimate is going to be below the original value. That's why it's an underestimate value. And if we talk about the midpoint, this is going to give us a extremely good approximation, because so whatever we have lost out by not considering that area is going to be compensated by this extra area. So this midpoint approximation is an extremely good approximation, and we will be doing some numericals and we'll be comparing the values for each of the 3 approximation, and we will observe that the midpoint approximation gives us a really good value, very much closer to the original value that we want. So let's perform some numericals. Problem number 1, we need to find the approximate area under the curve f of x equals to x squared on this given interval 1 to 4. using the right endpoint, left endpoint, and midpoint approximation. And here 4 represents, this is the n value. That means we have to consider 4 rectangles. So let's begin. We'll start with the right endpoint approximation. For this, first, let's try to sketch the graph of fx equals to x squared. So that means we want to find the area under this graph x squared and lying between the interval 1 and 4. Since we have n equals to 4, we will divide this into 4 rectangles. Now what will be the width of each rectangle? So the width can be obtained as delta x equals to, so our endpoint B is 4 minus endpoint A, which is 1, divided by how many rectangles? 4. So we divided by 4. So this is the value of n. So this gives us 3 over 4. So that means the width of each rectangle is going to be 3/4 or simply 0.75. Now since we are going to perform a right endpoint approximation, so for each rectangle we consider the rightmost point on the curve and construct a rectangle with that endpoint as one of the vertex of the rectangle. So we'll try to find out the area of each of this rectangle. So we'll begin with this first rectangle. So using the formula for the right endpoint approximation, r underscore 4, so this will be equals to, so we have, let's write down the formula first, delta x multiplied to, so we have f of a plus delta x plus, this is for the first rectangle, this is the smaller rectangle, then we have the second rectangle, a plus 2 times delta x plus f of a plus 3 times delta x plus f of a plus 4 times delta x. So here delta x is 0.75. Then we have f of, what is a? A here is 1. So we have 1 plus delta x, so that is 0.75 plus f of 1 plus 2 times delta x, so that will be 2 times 0.75, which is 1.5 plus f of a plus 3 times delta x, so this will be 2.25, and for the fourth rectangle we have the height 1 plus 3. Right. Let's complete the calculation. So this will be r underscore 4 is equals to 0.75 multiplied to f of, so this is 0.75. So recall our function f of x is given by x squared. So f of 1.75 will be 1.75 squared plus 2.5 squared plus 3.25 squared plus 4 squared. So we'll substitute all this value and this is going to give us 26.9065 square units. So this is going to be the area under the curve fx equals to x squared within the interval 1 and 4. And since we are using a right endpoint approximation, so this is going to give us an overestimate. We'll check that out in a moment. So let's mention it here that this is an overestimated value. Now we'll go to the left endpoint approximation. So here we have divided the interval from 1 to 4 into 4 rectangles, equal rectangles, each of which the width will remain the same, delta x, which is given by 4 minus 1 divided by 3 divided by 4, which will be 0.75. Now we are going to use the left endpoint approximation. So consider the first rectangle and we construct a rectangle with that endpoint as one of the vertex of the rectangle. So this is our first rectangle. So our left endpoint approximation with 4 rectangles, so this will be equals to, so we have 4 rectangles, so we have 4 heights. Now let's find out the value. So we have 0.75 multiplied to, using a function f of x is equals to x squared, so f of 1 will be 1 squared, and this is going to give us a value 15.65625, and compared to the previous value, this is going to be an underestimate value. The reason behind this is we have excluded these portion of the area. We have not counted this. We have not factored in this extra rectangular areas, extra area under the curve, because of which we are getting an underestimate value, which is far below the original value. Now let's talk about the midpoint approximation. So here we have divided the area under the curve f of x equals to x squared within the interval 1 and 4 into 4 equal rectangles. The width will remain the same, 0.75. And this time we're going to consider, this is our first rectangle. We're going to consider the midpoint here and draw a rectangle such that the width of this rectangle passes through this midpoint for the first rectangle. So this point will be, so we have 1 plus delta x, so that is 0.75. So this will be 2.5, and this point will be 2.5 plus another 0.75, so we'll have 3.25. Now in the interval 1.75 and 2.5, we will consider a midpoint between the curve and then construct another rectangle passing through that midpoint. For the third rectangle, we will have this rectangle, the width of this rectangle passing through this midpoint. And similarly, for the fourth rectangle, we draw another rectangle whose width passes through this midpoint. So the midpoint approximation with the n value of 4, this will be equals to, the delta x is 0.75. This will be multiplied to f of a. So a here is 1 plus we have delta x 0.75 divided by 2, which is 0.375 plus f of 1 plus, so we have 3 delta x divided by 2, so this will be 1.125 plus f of a plus 5 delta x over 2, this is 1.875. A here is 1 plus f of 1 plus we have 7 delta x over 2, so this is 2.625. So this gives us the midpoint with n value of 4, 0.75 multiplied to, so we have f of 1 plus 0.375, so this is 1.375, and using a function f of x, this will be 1.375 whole square. For the second one, we have 2.125 squared plus 2.875 squared, and for the fourth one we have 3.625 squared, and when we calculate this value we get 20.859 square units. Now the actual value of the area, so that's equals to 21 square units. And of all the three values, we can see here that our midpoint approximation is very much closer to the original value. This is 20. If we look at the left endpoint approximation, it's quite far away from the original value. So this is an underestimate value. And if we look at the overestimate value, that is the right endpoint approximation, this is quite above the original expected value of 21. So it's an overestimate. This is how we can perform the right endpoint, left endpoint, and midpoint approximation to find the area under a given curve for that particular interval. So let's try out another problem. Problem number 2. We need to find an approximate area under the curve f of x equals to 1 over x on the interval 1 and 2 using a right endpoint approximation, left endpoint approximation, and the midpoint approximation. So we'll begin with our right endpoint approximation. So we have this the function 1 over x, and we want to determine the area within the interval 1 and 2 under this particular curve. So here we're going to use the right end approximation. So we have drawn 3 rectangles. That's because our n value is equals to 3. So from here we can also obtain the width of each rectangle, delta x value, which will be equals to 2 minus 1 divided by 3. So this is going to be 1/3. Right. So let's use the formula for the right end approximation. So we have, in place of delta x, 1 over 3, multiplied to f of a. So a here is 1. So 1 plus 1/3 plus f of 1 plus 2/3 plus f of 1 plus 3/3. This will give us 1/3 multiplied to f of 4/3 plus f of 5/3 plus f of 6/3, which is 2. Now we have f of x given by 1 over x. So f of 4 over 3 will be 1 divided by 4 over 3, so that's 3/4. Similarly, f of 5 over 3, this will be 3/5, and f of 2 will be 1/2. And when we plug this into a calculator, we get the value 0.617. Now, in the previous problem, when we were calculating the area using the right endpoint approximation, we got an overestimate. But in this case, this is going to be an underestimate. This is an underestimate value. That is because if we look at the diagram, so we have left out some areas under the curve. So all the shaded areas under the curve has been left out. So we are not exactly getting the accurate value of the area, but it is going to be a little below the original value. So this is going to be an underestimate value. So depending upon the problem, so we have to be careful which one is giving us an underestimate value and which one is giving an overestimate value. So in this case, the right endpoint is giving the underestimate value, and we will see that the left endpoint is going to give us an overestimated value. So let's try that out as well. So we're going to perform the left end approximation. So here, delta x value is 1/3. We have f of a, so a value is 1, plus f of 1 plus delta x, which is 1/3, plus f of 1 plus 2/3, which will be 1/3 multiplied to f of 1 plus f of 2/3 plus f of 5/3. For f of 1, we have 1. F of 2 over 3 will be 3 over 2, and f of 5 over 3 will be 3 over 5. And this is going to give us a value approximately equals to 0.783. And this is going to be an overestimate because we have considered some extra area which is above the curve. So these is going to be some extra values of area above the original value. Now let's talk about the final one, which is the midpoint approximation. So let's consider the midpoint approximation. So here we have considered 3 rectangles with one of each of the width passing through the midpoint. So let's plug in the values. We'll have 1/3 multiplied to f of 1 plus 1/3 over 2, so that's 1/6, plus f times 1 plus, so we have 3 times 1/3 over 2, so that will be 3/6, plus f of 1 plus, we have 5 over 6. So this should give us 1/3 of f of 7 over 6 plus f of 9 over 6 plus f of 11 over 6, which is 1/3 of 6 over 7 plus 6 over 9 plus 6 over 11, and plug this value into a calculator, and this should give us 0.68975. And the area, this area is actually natural log of 2, whose value is 0.6931. As expected, we can see that the midpoint approximation is giving us a value which is very much closer to the actual area under the curve. So this is how we can use the different methods, the 3 approximating methods, to calculate the area under a given curve. So see you in the next class.